Simpsons rules are other numerical integration methods in which a second order function is used to predict the function and the integration of the function. So basically higher order polynomials can be used for better accuracy. The Simpsons 1-3 rule has this kind of parabola actually for prediction of the function. Then we get the area under this parabola, which is a second order function, and that area gives an estimation of the area under the real function. So, but for applying this Simpsons 1-3 rule, we need an additional point. If you remember, in the trapezoidal rule, it was a linear approximation from the limits a and b, like this. But in this, we need one more point. 3 points we need to be able to pass through a parabola from them. So if there is a point between FA and FB, FA is here, FB is here, there should be another point between them. 3 points are connected with a parabola, second order polynomial, then we can use Simpson's rule to get the integration. There is also Simpson's 3-8 rule, and in this we are actually fitting a quadratic polynomial, a third order polynomial. That means we need one more point. So we will have 4 points, you can see. This is the real function, and we have a and b as well as 2 more points in between these ones. Then the predicted quadratic function, which is shown by dashed line, is passing through all these points, and the area under it gives the estimation for the integration of the actual function. And the reason of 3-8 rule and 1-3 rule meanings, we will show that reason in the following slides. But in here, you should only know that 1-3 rule has second order polynomial to 3 points, and the Simpsons 3-8 rule has third order polynomial and 4 points. So let's go to the next slide to further understand the 1-3 rule first, then 3-8 rule. In the Simpsons 1-3 rule, we are going to use a second order interpolating polynomial for integration. Basically, we predict the function with a second order polynomial. And for that, we can use Lagrange polynomials and a second order Lagrange polynomial. You can see here, if you remember, the second order Lagrange polynomial has these 3 terms with 3 points. So x0 and x2 are the a and b, the limits, and x1 is in between them. And simply, the result of the integration is, when you take the integration of this with respect to x, between x0 and x2, which are a and b, the simplification becomes like this: h over 3, fx0, 4 fx1, and fx2. And in here we assume h is b minus a divided by 2. And if we put this into h, it becomes b minus a, and this 3 is multiplied by divided by 2, it becomes 6. So top part is this, and this is actually width of the area, and the average height is this. Basically, when you multiply these, it gives an estimation of the integration. x0 is a, x2 is b, the limits, x1 is a point midway between a and b, which is given by a plus b divided by 2. So it is in the middle, exactly. And because we have 3 points, it's 1-3 rule. 1-3 comes from this divide by 3, actually. 1-3 division exists here, so that's why it's called 1-3 rule. For the error of Simpsons 1-3 rule, we will have the same idea of the Taylor series expansion, because we actually have a parabola which is a second order polynomial. After the second order, we need to truncate the function, and the rest will be our truncation error. But there is something unique for Simpsons 1-3 rule. Even though it is a second order polynomial, the truncated portion, the error, actually has the fourth derivative instead of having the third derivative. So this is a unique feature. That's why it is very accurate actually. And the error, true error, is given with this h5 and fourth derivative. And here the psi lies somewhere in the interval from a to b. We say that already, always. And so instead of h here we can write b minus a divided by 2, then it becomes 288. So this is the final function actually. So when we compare this with trapezoidal rule, which has the true error of this, you can see that this has to the power 3, this has to the power 5. So this is more accurate, and it's one magnitude more accurate. So it's not 4, because after this is first order polynomial, this is second order polynomial, but this has 3, but this has 5 instead of 4. Similarly for derivative, this has the second derivative. We expect this to have the third derivative, but no, it has the fourth derivative. So when we compare them, the trapezoidal rule indicates that it's more accurate than expected. So the comparison with trapezoidal rule shows that the Simpsons rule is more accurate than expected because of this one more higher order actually than expected one. So rather than being proportional to the third derivative here, the error is proportional to the fourth derivative, you can see. So Simpsons 1-3 rule is third order accurate, even though it is based on only 3 points. In other words, it yields exact results for cubic polynomials, but it is derived from a parabola. So because this has the fourth derivative here, rather than predicting the second order functions exactly, it can predict the third order functions exactly as well. So that's the unique feature of it. Even though it is a parabola, a second order polynomial, it can give exact results for integration for cubic polynomials. This is a unique feature. And for the approximation error, when we don't know the true error or true value, the approximation error is the same, and we can simply write it as minus b minus a 5 divided by 2880. But for this, because we don't know this, instead of that we are taking the average of this fourth derivative, which is similar to, if you remember the trapezoidal rule, we were taking the average of or mean of this. Now we are taking the mean of the fourth derivative, which gives us this 4x, and this shows the mean actually. We will use the mean function. We will show this calculation of error in the example for Simpsons rule in the following slides.